Hello, AP Chemistry 12. This is Mr. Chan, and today is the second lesson in terms of talking about integrated rate laws. Now, remember last day when we talked about rate laws, what it is when we talk about rate laws, we're talking about rate in relation to how it relates to concentration. And what happened is we compared that with how we did rates in Chemistry 12. For Chemistry 12, remember the rates was a change in concentration or change in moles or something over change in time. While rate, when we did AP using the rate law equation, was just solely based on the concentration. Okay, notice there's no change in time in the formula. But both ways do calculate the rate of a reaction. Now, when we talk about rate of a reaction, one thing I want to talk about is the definitions of rate. Now, there's three different definitions of rate. One is the average rate. Now, when we talk about the average rate, it's the change in the amount of product or reactant over an interval of time. That's what we focused on when we did Chemistry 12. Okay, so if we take a look at this, this is in Chem 12. Now, if we were to take a look at a concentration versus time graph for a reaction, you will notice as an exponential decrease. And what average rate would be either line D or E. Okay, so you could say, look at line D or E. Not door, but D or E. Okay. That would be the average rate because you're taking the change in concentration over change in time. Now, another type of rate that we can talk about is something called instantaneous rate, a rate at a particular time. It is obtained by taking the straight line tangent that touches the curve at the point of interest. Now, in this case, it would be either B or E, or C, sorry. That would be called the instantaneous rate. And the initial rate is the instantaneous rate at the beginning of the reaction. This would be represented by A. And this is what has been the focus when we use to calculate the rate law. Okay. Now, the problem with doing rates and measuring concentration over time is you notice it's an exponential curve. And it'd be very difficult to sort of get an instantaneous rate because the tangent line could be different depending on one's perspective. So to make life a little bit simpler, what we do is we need to sort of modify our rate equations to compensate for this type of decrease. And so what we use is we use something called the integrated rate laws. Now, for a first order reaction, recall rate is equal to either the change in concentration of A over change in time, or rate is equal to K, which is the rate constant, times the concentration. Again, recall this is what we focused on in Chem 12. This is the rate law for AP Chem. Using calculus, the rate equation can be transformed into an equation that relates the concentration of A at the start of the reaction, A to the 0 or A initial, to its concentration at any other time t, concentration of A at time t. This is called the integrated rate law. Okay, so using calculus, they integrate the equations, and when we integrate it, we can use either natural logarithms, natural log, okay? Or we could use normal log or log base 10. Now, rearranging the natural logarithmic equation, one can obtain this equation. Natural log of the concentration of A at time t is equal to negative k t plus natural log of the original concentration of A. Now, one thing you should be aware of, okay? This equation, what happens is it is given. You're given this equation on your AP exams. So you don't need to memorize it. You don't need to know how this works. You'll be given the equation. It's just you need to know how to use it. Okay? Now, what's the significance of this equation? So this equation has the form of the general equation for a straight line graph. Y is equal to mx plus b. Okay? So what's the significance of this? So if we take the natural log of the concentration of A at time t and put it on our y-axis, and then the negative k, this is our slope, and the t becomes our x-axis, and this one here, the natural log of the original concentration of A, this is the y-intercept. Now, what's the significance of this is that it changes this exponential decrease in concentration versus time. What happens is that it creates a straight line graph. And so what we have with a straight line graph is we're able to calculate the slope, which is the rate constant, and we can accurately determine at any given time, we are able to figure out the exact concentration of whatever substance we have. Okay, so instead of any of the uncertainties with this exponential decrease in concentration over time, we've changed it into a linear graph where we're able to get more accurate results. Okay, now, one thing with about first order reaction, we want to talk about something called half-life. And some of you may have been exposed to this in geology. Okay, but what is half-life is the time required for the concentration of a reactant to drop to 1/2 of its initial value. Okay, and that's what I have in the equation here. Concentration of A at T1/2 is equal to 1/2 of the initial concentration. That's what we call the half-life. Okay, so the time that it takes. Okay. Now, by looking at the equation, what I want you to do is I want you to focus on this last one. Again, this one is given. Notice the T1/2, so the time it takes for 1/2 of the concentration of the reactant to drop, for a first order rate law is independent of the initial concentration of the reaction. So notice it says here, the T1/2 for a first order rate law is independent of the initial concentration of a reaction. Notice there is no concentration present in the equation. So what does that mean? So what that means is that for a first order reaction, doesn't matter where you start, to get to 1/2 of the original concentration, it's always going to be a set time interval. So if we were to graph the half-life of something, we will notice that the T1/2, the time it takes to go from the original concentration to 1/2, it's at a set time. There is no deviation. Okay? Now, some of you have been exposed to that in, let's say, carbon dating, or when you talk about radioactivity back in grade 10. What happened was the half-life, it did not matter what concentration or amount of substance you started with, the half-life was always constant. And that is characteristic of a first-order reaction. Okay? Now, for second-order reactions, where rate is equal to a to the power of 2, and that's why second order, okay? What you will notice is instead of natural logs, we just use the inverse concentration. So in this case, again, if we have 1 to the over the concentration of A at time t, this will be my y-axis, k will be my slope, and t will be my x. Again, what that does is that creates a straight line graph so that we are able to predict at whichever time we are able to predict what the concentration would be. Okay? So what the integration basically is to change an exponential decrease in the curve and make it into a straight line graph. And again, using the above equation, one can show that the half-life of a second order reaction is this. Now, notice for a second order reaction, the T1 half is dependent on the original concentration of your reactant. Now, when you look in your Zumdahl 9th edition book, okay, if you take a look at this, the integrated rate law starts on page 563, so section 12.4. Now, as you go through it, they do talk about it in a little bit more detail. But what I want you to do is focus on page 574. Now, if you take a look on page 574 in your Zumdahl 9th edition, what you will notice is that there's a table summarizing all of the different rate laws, the integrated rate laws, and the plot needed to get a straight line. So my suggestion would be make sure you are familiar with section 12.6 in terms of what are the characteristics for first, second, and zero order in terms of the integrated rate laws and the plot needed to give a straight line. And again, you don't need to worry too much of how do you go from one to the other in terms of how do you go from rate law to integrated rate law, but you should know how to use the equations. Okay? Now, so if I were to do a question, its typical question would be something like this. The first order rate constant for the decomposition of a certain insecticide in water is 12 degrees Celsius. At 12 degrees Celsius is 1.45 per year. A quantity of this insecticide is washed into a lake on June 1st, leading to a concentration of 5.0 times 10 to the negative 7 grams per centimeter cubed of water. Assuming that the effective temperature of the lake is 12 degrees Celsius, answer the following question. So for A, what is the concentration of the insecticide on June 1st of the following year? The first thing that you will notice is that this is a first order reaction. Okay? So for a first order reaction, we use natural log concentration of A at time t is equal to negative kT plus the natural log of the original concentration. So in this case, we just plug in the numbers. So here is negative 1.45 per year times 1 year, because that's from June 1st to June 1st, plus the natural log of 5.0 times 10 to the negative 7. Okay. Now, so what we can do is we can, plug in the numbers. And what do I get here? I get 5.0 e, oopsie, natural log 5.0 e negative 7. So here I have minus 1.45 plus minus 14.51 minus 1.45, oopsie. And I get an answer of minus 15.95. Now that's the natural log of A at time t. To calculate the concentration of A, what we do is we take the natural inverse log minus 15.95. Now, some of you might say, wait a minute, how do we get this? Where'd you get this little thing E here? If you look on your calculator, okay, depending on what calculator you have, what you have is you'll, on a graphing calculator, you will have this natural log. The E button that I was talking about is the one right above it, right here. Now, for those of you with not a graphing calculator, what you have is you have the natural log button right there, and you have the E right above it. Okay? So if we have that, you take the inverse natural log. And if I take the shift that, I get the answer is, oopsie, 1.17 times 10 to the negative 7. Okay? So that is how you find the concentration. So that is for A. Now for B, it says how long will it take for the concentration to insecticide to drop to 3.0 times 10 to the negative 7? We use the same equation, but we just plug in the numbers. So here would be 3.0 times, oopsie, I'll start here. So natural log of concentration of A at time t is equal to negative KT plus natural log of A to the 0. So I take the natural log of 3.0 times 10 to the negative 7 is equal to negative 1.45 year times t plus the original concentration is 5.0 times 10 to the negative 7. Natural log 5.0 times 10 to the negative 7. Okay, so 3.0 e to the negative 7, natural log, oopsie. So this would be negative 15.02 is equal to negative 1.45 t plus negative 14.51. So negative 1.45 t is equal to 15.02 negative 0.511. So t divided by 1.45, that would be 0.35 years. Okay, so hopefully that was pretty straightforward. Now, if you were to take a look at your Hepton reading package that I gave you, okay, The integrated rate laws and that sort of stuff actually starts in section B. Okay, they talk about logarithms, okay? And then you talk about first order reactions, the natural log. And if you were to take a look at your Zumdahl reading, what it does is start at section 12.4. So my recommendation is as you go through this, if we scroll down here, I would recommend that you take a look at, in the Hebden, I would go from B to G, I believe. And then for the Zumdahl, I would like you to do section 12.4. Okay, which I believe that's the case. Scroll down just to double check. Okay. Yeah, section 12.4, the integrated rate law. All right, ladies and gentlemen, thank you very much. Have a good day.